kinetic plus potential equals kinetic plus potential. Now, because I have rolling going on, because the rolling will be changing as it comes down the ramp, because there's friction, as it speeds up in the linear direction, it will speed up in the angular direction. So I have two types of kinetic energy. I have the translational, or linear, plus the rotational, or angular. Because the only force acting on it that's doing any work is the force of gravity, we're dealing with gravitational potential energy. Oops, that should be a final R, and then apparently switching notation about where to put the F or the I. So we have 1/2 mv initial squared plus 1/2 I omega initial squared plus mghi equals 1/2 mv final squared plus 1/2 I omega final squared plus mgh final. We can simplify it because it's a hollow sphere. Yeah, it's a hollow sphere. So I look up the moment of inertia of a hollow sphere. So I have 1/2 mvi squared plus 1/2 times 2/3 m r squared omega I squared plus mgh initial equals, and then same over here, except I have a subscript f now, times 1/2 mv final squared plus 1/2 times 2/3 mr squared omega final squared plus m. And you know what? I'm just going to make that 0 because I say so. I have r squared omega squared. Well, that, if it's truly rolling, that's just equal to the linear speed. So that's vi squared. Over here, that's vf squared. Now, some people like plugging in the numbers early, and that's fine because I give you the radius, but if I didn't give you the radius, then you should still be able to do this type of problem. So I have 1/2 mv squared and then 1/3 mv squared, so I get 5/6 mv initial squared plus mgh initial is equal to 5/6 mv final squared plus mgh final. No, that's right, I got rid of mgh final. I now have mass in every term, I can get rid of it. But if you plug in numbers, you would not be doing this step. We're trying to find VF. So let's isolate it. Multiply times 6/5. And then I would take the square root. So I basically have mv, sorry, I got rid of my m's already. My v initial squared plus 6/5 gh initial, and then square root. And so that is h, and I got 9.0525 meters per second. All right, so A at the bottom of the ramp here is now going to this speed right here. It's going to crash into B in a perfectly inelastic collision. So we've got to work one of those into the problem. And so I basically have A here traveling at 9.0525 meters per second. crashing into B, which is initially at rest. And that needs the numbers. Mass of A is 3 kilograms, mass of B is 7 kilograms. So my total momentum is 3 times 9.0525. This is my initial momentum, plus 7 times 0. Initial momentum equals final momentum, which will be the combined mass, because it's perfectly inelastic, 10 times the final. So whatever that is, oh. And this was, what's wrong going on? I. So 2.7158 meters per second. So I now have this 10 kilogram mass going at that speed, hitting my spring, and the spring is going to compress a certain distance. And so the next question is, how far will it compress? Well, I got conservation of energy again, except this time with a spring. E initial equals E final. K initial plus U initial equals K final plus U final. I'm not dealing with any change in height, so my potential energy is because of the ideal spring. Now, A is officially still rolling, but whatever rotational energy it has, because the bottom surface down there has no friction, the rotational energy, kinetic energy, doesn't change. So it has some value, but it's just going to cancel out, so I'm not going to worry about it. The I squared plus 1/2 K delta X squared initial is equal to that, except final, 1/2 mv final squared plus 1/2 K delta X squared final. Well, that's 0, and that's 0. I know the final speed is 0 because it's maximum compression. And so what I'm left with is, well, the halves can go away. So I have mv initial squared is equal to K delta X final squared, or delta X final is equal to m over K square root times VI. Divide by K, get the square root. And so that is the square root of 10 divided by the spring constant, which is given 20, times how fast it was going, 2.7158. That's 10 kilograms, and this is 20 meters per meter. See, that was J. And so we end up with compression of 1.92038 meters. So it's basically hit the spring and it's now oscillating back and forth. The next question is, what is the period? The period does not depend upon the amplitude or the maximum compression. It does depend upon the mass and the value of the spring constant. How much mass are we moving and how stiff is the spring? This is a formula. Or I guess potentially you could derive it if you got loads of time. T is equal to 2 pi times the square root of m over K. This K right here is the spring constant. The more mass it is, the longer it's going to take, so time would go up. The stiffer the spring, the less time it's going to take, so as K goes up, it's in the denominator. It means I've got a smaller fraction. So this is 2 pi times the square root of 10 over 20, which ends up being 4.4425, assuming I can read my handwriting. All right, so A and B will hit the ideal spring and compress it. The spring has a rope attached to it, yada, yada, yada. That's not the important part. After the compression, A will separate from B. Reword that. B will stick to the spring, but any stickiness between A and B will disappear as soon as they hit the spring. In other words, so we got B right here, A comes in, hits it, they stick together, they hit the spring, and as soon as they hit the spring, they're no longer attached to each other. They will still move together, because they're going the exact same speed. The only thing slowing them down is, well, this is being slowed down by the spring, and this is being slowed down by B. It'll stop, it'll come back, and because they are not attached to each other anymore, are not connected anymore, they're still touching. When the spring gets back to equilibrium, that's the point in which the spring will start to slow down and slow B with it, but A will keep going. And so question L is the instant before A and B stop touching, how fast are they going? In other words, how fast is A going when they get back to equilibrium? Well, it better be how fast they're going when they first touch the spring. It's the exact same number, the 2.7158 meters per second. Because energy is conserved here when they're touching the spring. So whatever energy they had here must be the same energy when they get back there. So after A goes separated, the M is then asking, as the spring what changes? Because now it's just now it's just B touching this, attached to the spring, moving back and forth. The spring constant doesn't change. It's the same number as before, it's 20 newtons per meter, because the masses don't change the spring. Has the period changed? Yeah. The speed hasn't changed. I know how fast B is going, but the mass has changed. The spring is now moving less mass, so I would expect the period to get shorter. And so the period will change. And so it's 2 pi times the square root of 7 divided by 20. Let's see, this is M2. Okay, so that was the period, but now with A gone, it's 3.7172 seconds. What about the frequency? Well, if you know the period, I know I can find the frequency easily enough, because the frequency is just 1 over the period. 0.269 hertz. And then the angular frequency, again, just straight up formula. Angular frequency is 2 times regular frequency, so it's 2 pi times 0.269. 1.6903 radians per second. And then the question is, what's the equation? I have the 7 kilogram mass that's oscillating back and forth. Yeah, 7 kilogram mass. And the equation, there are a couple ways of doing this, but it really comes down to, at what point do you want to start the clock? Do you start the clock when B first hits the mass, or when A first separates, or do you start it when it's at maximum compression? Because it makes a difference in terms of what trig function you can use. So I'm going to choose sine, because sine starts at 0, cosine starts at the maximum, sine starts at 0. And so x should be the amplitude, which we have right here. 1.92038 meters, times the sine of the angular frequency, which we have right here, 1.6903 radians per second, times time. So now I have the spring oscillating back and forth described by this. Basically, it's now wiggling this rope back and forth. So the next question was, how fast, what is the speed of the wave in the rope? Well, I've got two equations for that. I pick whichever one's gonna work. I've got frequency times the wavelength, which isn't gonna work because I don't know what the wavelength is yet. And that's also equal to the square root of the tension divided by the linear density. And coincidentally, I just happen to give you both numbers. So that's the square root of 20 newtons divided by 0.1 kilograms per meter. And so this was 14.421 meters per second. Now here is a small mistake in this. This is you got more in line with the common language on this one. It actually should say third harmonic instead of second harmonic, because I basically have a fixed end, that's a node, and I have a free end, because this is oscillating its maximum amount. So this is similar to the speed of sound water tubes that we used in a demonstration. The first harmonic looks like this, fixed end, free end. The second harmonic, what I was referring to here, was just the second one that you can produce. That was the intent. That is drawn really badly. Marginally less badly. I know the speed of the wave. I can now figure out the wavelength, because I know that that is 3/4 of a wave. Is equal to whatever the length of this is, which, oh, nope, that's what we're trying to find. So that's what we're gonna need for the very last question, but the question P is, I know what the speed is, the frequency. In other words, how long does it take for the end of the string to go down and back to where it started? It's the same frequency as for the spring. The spring is creating this oscillating rope here. And so this is equal to my frequency, 0.269, hertz, times the wavelength. And so the wavelength would be 14.421 divided by 0.269. Okay, 52.569 meters, it is a length. And then the last one is, what's the length of the rope? Well, it's 3/4 of that. Now, for some reason, when the students did this, they were not wowed. And I know I just spewed a whole lot of stuff very quickly at you, but at least all of this is stuff that we have done before in class. The written up solutions in some orders also listed online right next to the desk. If you go to the old test and you scroll down, eventually you'll find one that's the Rube Goldberg test. And as a matter of fact, there's a arrow pointing at it saying, this is the Rube Goldberg test, or something like that, with the answers and then the solutions also. Now, because this is so dependent on so many other parts, in theory, I could just look at this last one right here and I'd have a pretty good idea of, there are a couple of places where, like, this one was sort of offset, but if this were correct, then I pretty much knew everything else was, other than I'd have to look at that. It's actually incredibly easy to grade. One, because I had a spreadsheet, all I have to do is type in the number that you got, and it immediately populated all the rest of the answers, what your answer should be. And two, unfortunately, too many people left stuff blank. And so there's the psychological factor that I usually forget about. So what I did though is I said, if you can't do a part, just use the number that I gave you. I gave you a number right here. Now, I did that for this one because it was so incredibly dependent upon itself, but if you're ever in a situation where you can do another part here, then, I mean, if you knew the period, you should be able to find the frequency, they're just reciprocals. And you go, oh, I know how to do that, I don't know what the period is, well, just use this number right here. I will see the number that you used. So, now, I'm not providing that on this test because it's not, several dozen parts all related to themselves. But if it's more than one part and you can't do part A, but you know how to do part B, if only you can do part A, please make up a number, not 0. Show me that you know how to do it. And then if later on you go, oh, I know how to do part A now, then just make a note, just say, I did part B, use this number, but then I figured out how to do part A. Here's how to do part A, do part A. You don't have to go back and redo part B, unless you want to. And some students do. So anyway, that is half the course right there in a half hour. It's so simple. A child could do it. I was quoting